Hi everybody, this is lecture 3 about motion. So, what is motion? Motion can be complicated if you consider spin or air resistance or a bunch of different things. But in general, it's an object moving through space. Now here on Earth, we have air everywhere, and that complicates the problem of motion because the air is always causing resistance to motion. And air resistance depends on complicated things like mass distribution and surface area and different things. So it's very complicated. A lot of the time we can talk about air resistance in abstract terms, but to get real numbers is very challenging. So in this case, in our class, we'll talk about air resistance only in terms of maybe general effects it has on motion, or we'll ignore it altogether. An example where air resistance is important would be dropping a piece of paper where it sort of floats down versus a crumpled piece of paper where it just falls like a rock. Okay, and the difference is air resistance, very complicated. But we can remove the complications. Well, if we can remove the complications, there's very simple relationships a lot of the time. We'll talk about these relationships. All motion is relative, but so for us, unless we state otherwise, we're going to do all our motion relative to the Earth. That means if we're moving at 50 miles an hour, that's 50 miles an hour relative to the ground. Or if we're running at 5 meters per second, we're running relative to the ground. Okay, but we don't always have to think of it that way. We could have the Earth relative to the sun. We could have the sun relative to the galaxy. We're not often going to worry about that. So we'll do us on Earth. We'll do cows on the side of the road and person on the subway, all relative to Earth. Okay, so what is speed? When you're moving, when an object is moving or you're moving, we have this thing called speed. What is speed? The idea is it's a rate of change of position. And the units for speed are meters per second or kilometers per hour, miles per hour, feet per minute, things like this. It's a distance covered per time. There's also the idea of an instantaneous speed, where that's the speed you have at a particular moment in time. So if you're driving down the road and you see 50 miles an hour on your speedometer, that's 50 miles an hour right at that moment in time. The other type of speed is average speed, where it takes the total distance covered divides by the time it took. Okay, so if I was driving, say, from Sacramento to San Francisco and it took me 2 hours, from that I could calculate my average speed by the distance from Sacramento to San Francisco divided by time. I might get something like 40 to 60 miles an hour depending on the traffic. Okay, so let's do a quick question here. The average speed of driving 30 kilometers in 1 hour is the same as the average speed of driving 30 kilometers in half an hour. Same distance, different time. That's not right. 30 kilometers in 2 hours, that's same distance, longer time. That's not right. 60 kilometers in half an hour, that's a different distance and a different time. That might work, but we're covering more distance in less time. That's faster than what we were doing. So 60 kilometers in 2 hours, that's the same ratio as 30 kilometers in 1 hour. So it looks like that's D. Okay, so that's D. Okay, there's speed and then there's velocity. Velocity is the same idea as speed, but it has a direction attached. So if I'm driving in my car and I'm going 50 miles an hour, that's my speed. But if I'm going 50 miles an hour north, then that's my velocity because I put a direction on it. And that means velocity is a vector. That means it's an arrow pointing in some direction. Okay, and when you have an arrow, there's a couple different ways to change an arrow. You could change the speed, which would lengthen the arrow or shorten the arrow, or we could change the direction of the arrow, or we could do both. Okay, so velocity includes direction. So a speeding up and a slowing down or a changing direction all changes velocity. Okay, this brings us to the idea of acceleration. Acceleration is the rate of change of velocity. And there are 3 ways to cause an acceleration. You could change the speed of an object, you could speed it up, or you could slow it down. So in your car, if you're driving along, or you're in a bus driving along, and the driver hits the accelerator, then you speed up. That's an acceleration. If the driver hits the brakes, the acceleration's in the other direction, of the motion of the bus or the car, and that slows you down. That's also an acceleration. If you're in a vehicle and a person turns the wheel and it keeps constant speed going around a corner, then that's also an acceleration because the velocity is changing direction. And you could do combinations. You can go around a turn while accelerating. You can go around a turn while braking. These are all accelerations. Okay, if we just restrict ourselves to a straight line, then this blue box here tells us that acceleration along a straight line is the change in speed over how long it takes. So speed is how much distance you covered per time, not worrying about direction. And acceleration along a straight line is how much did your speed change over a certain amount of time. Okay, so let's talk about just acceleration along a straight line, not worrying about changes in direction. So the units for it are meters per second squared, or meters per second per second. So it's how much speed in meters per second has changed per second. Acceleration due to gravity, we learned last lecture, is 10 meters per second squared. And acceleration is a vector. It has a magnitude and direction, so you can point the acceleration in a bunch of different directions. But if we restrict ourselves to straight line speed or straight line motion, we can relate the directions of velocity and acceleration. So for example, if you are in a car and you hit the acceleration is in the same direction as velocity. We call that accelerating or speeding up. If we're in a car and we hit the brakes, then our velocity is forward, our acceleration is, well, let me do this right. Velocity is forward, acceleration is backwards. These are in opposite directions. We call that decelerating or slowing down. Both of those are types of accelerations. And the difference is the acceleration with your velocity, or is the acceleration against your velocity? Okay, an automobile is accelerating when it is slowing down to a stop. Yep, that's accelerating. Rounding a curve at a steady speed, that's also accelerating because the direction's changing. So it sounds like C, both. Okay. Acceleration and velocity are actually the same. Well, they're not the same. Velocity is speed and direction. Acceleration is how much your speed is changing over time and a direction. Both are rates of change, but for different quantities. That sounds right. The same when direction is not a factor. I'm not sure that means anything. The same when an object is freely falling. That's not true. So B. Okay. Okay, this is a bit of review. Mass versus weight. So mass is how much matter is in an object, and weight is the force of gravity on an object. Okay, we'll talk about free fall and non-free fall. So when something is in free fall, it only has weight acting on it. So here's a rock right here, force of gravity acting down on the object, and there's nothing else. That's free fall. And if we remember from last lecture, the force of gravity is mass times the gravitational acceleration, which for us is 10 meters per second squared. So free fall is motion under the influence of the force of gravity only. No air resistance, nothing else, just gravity. That's free fall. If we drop two rocks of different masses at the same time from the same height, which one will hit the ground first and why? Well, if they're both in free fall, it's the same for both. But if there's air resistance, then the complications of the different surfaces of the rocks and the sizes of the rocks will determine which one hits first. If we drop a rock and a feather at the same time from the same height, which one will hit the ground first and why? Well, for this, air resistance is almost more important than gravity, so the rock will hit first, and the feather will do its air resistance thing. Okay, so non-free fall. So in free fall, the acceleration on Earth is 10 meters per second squared. What factors affect air resistance? Well, the mass distribution and the area, and maybe even other things like the texture of the surface. There's this idea of terminal velocity, and that's when you fall, if you jump out of an airplane or you throw something from a very high height, then eventually the air resistance will cancel out the force of gravity, and it will not accelerate at all during when it's falling toward the ground, whatever object that is. So the big factor in determining terminal velocity is air resistance. So if you are skydiving, which I've never done, but some people have, if you have your if you fall with your belly first, I think the terminal velocity is about 100 miles an hour, about something like that. So the air resistance will stop you from accelerating, and when the acceleration of gravity is down, the force of air resistance will oppose the motion, and eventually they will cancel out and you'll fall at a constant speed. Okay, let's get some questions here. When a 20 Newton, that's a weight. So Newton is the unit of force, and in the metric system, the unit of weight is a Newton. So 20 Newton, that's how much the object weighs. So when a 20 Newton falling object encounters 5 Newtons of air resistance, its acceleration of the fall is less than g, more than g, or terminated. Okay, it's not terminated. Since there's a little bit of air resistance, that's reducing the acceleration due to gravity, so it's going to be less than g. As a skydiver continues to fall faster and faster through the air, net force increases, decreases, remains the same, not enough information. Well, as the skydiver falls, they're speeding up, but they're getting more and more air resistance as they speed up, which means that the net force on them, which is causing the acceleration, is actually decreasing. Because at first, when they first jump out of the plane, only gravity is acting on them, so they're accelerating a lot. But as they speed up, that air resistance force is getting bigger and bigger and bigger, canceling more of gravity. When that happens, the acceleration reduces. Even though they're moving very, very fast, there's no acceleration, or it's getting smaller and smaller. So that's B, decreases. Okay. All right, so free fall. Okay, we already talked about free fall. Let's talk about acceleration in free fall. This is a bit of a review here from lecture 2. So the force of gravity divided by the mass is equal to g, and that's the same for all objects, whether it's a feather or a rock, assuming no air resistance, of course. And that's 10 meters per second squared. And so acceleration in free fall, if we throw a ball up in the air, the object is going to decelerate until it turns around, starts falling again. So something in free fall can go up and then down. Okay, and there's different aspects to this. When it's a car and we're moving horizontally, then acceleration is when we hit the gas pedal, and the velocity and the acceleration are in the same direction. When we're losing speed and we hit the brakes, the velocity and the acceleration are in different directions. It's the same thing with gravity. We're just going to make everything vertical. So accelerating, when you start speeding up due to gravity, is when you're falling down. So the velocity and the acceleration are the same direction, down. But when you're decelerating when free fall, then velocity is up, acceleration is down. So they're in opposite directions. So that makes sense. When you throw something up, it slows down, stops, and turns around. Okay. All right, so free fall, how fast? So here's a picture of a person throwing a ball upward. Starts at 30 meters per second, goes up a little bit, reduces its speed to 20 meters per second, reduces its speed even further to 10 meters per second. At the very top, this always happens. At the very top, the velocity is 0. It's not moving at all. And then it turns around and it starts speeding up in the downward direction. Okay, so it's initially decelerating, slowing down, going up, till it stops and turns around, and then it accelerates downward until it hits the ground. Okay, so what is 0 at the top? The speed or the velocity is 0 at the top. What is not 0 at the top? Acceleration. So the acceleration during this free fall trajectory, even though it's going up and stopping and coming down, is g the entire time if we ignore air resistance. And it's always down. G is always down. 10 meters per second down, 10 meters per second down, 10 meters per second down, no matter what. Okay, here's a question. A free-falling object has a downward speed of 30 meters per second at one instant. Exactly 1 second later, its speed will be the same. That's probably not true because it's in free fall, which means no air resistance. So it has to be accelerating down. 35 meters per second? I don't think so, because after 1 second, it should have increased by 10 meters per second because we're on Earth. More than 35 meters per second? That sounds right. 60 meters per second? That sounds like too much, because 10 plus 30 is 40, not 60. So I think the answer is C. Okay. A free-falling object has an upward speed of 30 meters per second at one instant. Exactly 1 second later, its speed will be, well, it's upward, it's moving upward now. Acceleration is down by 10 meters per second per second. So that speed of 30 is going to be reduced by 10. So it's not going to be the same. It's not going to be more than 30 meters per second. It's going to be less than 35 meters per second. That's true. It's certainly not going to be 60 meters per second. So I think it's C again. Okay. Now, free fall. How far if dropped from rest? So this is our equation right here for how far an object falls if it's dropped from rest. Okay, so the distance covered d is equal to 1/2 times g, which is 10 meters per second squared, times the time it's been falling. So here's a picture. After 5 seconds, it's covered 125 meters. This object that this person dropped. Okay, we can do any other value. We can plug in 2 seconds, plug it into here, we get 20 meters. Okay, we can do that for any time we want. And anything that's got a constant acceleration will follow this formula right here. This is the free fall formula for Earth. This is for any acceleration. Okay, a freely falling object starts from rest. What distance has it covered after 4 seconds? Okay, so we got that equation, 1/2 gt squared. So 1/2 times g is 5, and then 5 times t squared is 5 times 16, which is going to be 80 meters. Okay, looks good. Let's do some more questions. Suppose you hike a distance of 1 kilometer in a time of half an hour. Then your average speed is, so we're covering 1 kilometer in half an hour. That's 2 kilometers in 1 hour. That sounds like D, twice 1 kilometer per hour. Okay, that's right. When a ball increases in speed by the same amount each second, its acceleration is, so increases in speed by the same amount each second. So that sounds like a constant acceleration. The speed is increasing by the same amount each second. Its acceleration also increases each second. No, it's constant. Decreases each second. No, it's constant. Oh, C is constant. D fluctuates. It's not fluctuating. It's constant. Okay. The acceleration of a raindrop that falls at constant velocity is 0. If the velocity is constant and it's not changing, that's 0 acceleration. And none of these others are right because we know the acceleration is 0. So that raindrop must be at terminal velocity when gravity is canceled by air resistance. An object in free fall has a speed of 60 meters per second. 1 second later, its speed is, so it's in free fall. It's got a speed of 60 meters per second, but we're not sure, is it up or is it down? Okay, so we're not sure about that. So 1 second later, its speed is, well, it can't be 10, can't be 30, it can't be 60 because it's accelerating. It can't be 30 because in 1 second it should only change by 10. So it looks like it's D. So, and if it's D, that means it's 70 meters per second down. That means it was falling. It was falling at 68 meters per second. It sped up by 10 meters per second, and it got to 70 meters per second. Okay. The speed of a vertically thrown ball at the top of its path is, we know that's 0. That's the turnaround point. It's not moving at all up there. It's accelerating down, but it's not moving. Okay, and we know the others aren't correct because we know the answer is 0. Earth moves about 30 kilometers per second relative to the sun. When you jump upward in front of a wall, the wall doesn't slam into you at 30 kilometers per second. This is because the wall, well, this is inertia again from lecture 2. The wall and the Earth are moving together, and you are moving together at 30 kilometers per second. When you jump, you continue to move at 30 kilometers per second. You don't instantly slow down. And that's inertia, because objects in motion want to stay in motion, and that's why the wall doesn't slam into us. So let's see if there's this answer here. Has too little gravity to influence you. That's true, but kind of not relevant for the question. Moves in an opposite direction to you. That's not true. It moves with you. The wall and you are moving at the same horizontal speed before, during, and after the jump. That sounds like the one. And the wall has negligible inertia compared with the sun. That's true, but not relevant here, so C. Okay, and that's it. So I'll see you guys for lecture 4 next time. Have a good one.